Today we are happy to have Martin Sasieta from Brandeis.
Okay, thank you very much, Arlene, and thanks a lot for the invitation. I really enjoyed the first time on Berkeley. So today I'm going to tell you about some work which is related to the work that some people here in the department have been doing. And in particular, I'll be talking about the Python language. Okay, so the work that I'm going to talk about is based. Well, the work is mostly on this paper, which was put up on the archive in January. And this work was done in collaboration with Gurvir Arora, Matt Hedrick, Alvin Lawrence, and Conor Wolf, all of them who are at Brandeis. And I will also make some comments during the talk about some follow-up to this work that we are currently working on with the previous authors and with Brian Swing. So let me start with the very basic of this topic, even though probably most of you know about this. So in HEP-QIS, we are interested in understanding the map between the gravitational bulk effectiveness theory on top of some given background and the microscopic theory which leads to the asymptotic boundary of AES space. So this map is abstractly denoted by V, and it's simply some linear map which takes the information in the bulk and maps it to the microscopic inner space. Now, most of the progress in HEP-QIS over the last decade or so has been in trying to understand properties of this map. And in particular, one property that we think that we've understood, which is really nice and really profound, is that this map encodes the bulk quantum information in a very particular way. In particular, if one picks some spatially localized subregion in the boundary system, turns out that this spatially localized subregion has all the information of some subregion in the bulk. And this is called the entanglement wedge of the corresponding boundary subregion. So the entanglement wedge is delimited by codimension 2 minimal surface in the classical regime, which is called the Ryuta-Kanari surface, which you probably will have heard about. And the idea is that all the quantum information in big A in the boundary basically determines or knows about all of the quantum information in small a. Okay? And the main formula which ensures this property is the sort of quantum generalization of the Ryuta-Kanari formula, which says that the Von-Neumann entropy of the reduced state to the boundary subregion A is given geometrically by the area of this surface divided by 4 bar, and then there is some small correction coming from the entanglement of the bulk fields across the surface. Okay? So one thing that we've understood is that this formula is equivalent to saying that big A is dual to small a in this sense. In particular, explicit ways of formulating this duality have been provided, starting from this formula. An example is the so-called Betz map, which allows to reconstruct local operators in small a in the algebra of big A. So this is sort of the framework of entanglement wedge reconstruction, which has been useful in many different contexts. But a particular situation in which entanglement reconstruction is non-trivial is given by this sort of example, where the entanglement wedge of the boundary subregion extends beyond the region of causal accessibility of the boundary subregion. So there is another wedge which is smaller than the entanglement wedge, which is called the causal wedge. Okay? And the causal wedge is basically defined as the region of causal accessibility of the boundary subregion. And there are many situations, even in vacuum, in which the entanglement wedge of the boundary subregion extends beyond the causal wedge. Particularly in this case, for two intervals in ADS3, if the intervals are big enough, the entanglement wedge is in the connected phase, and it contains some region here which extends beyond the causal wedge, which is the union of A1 and A2. The causal wedge is delimited by some locally minimal surface, which is not globally minimal. And this is the reason why the real diagonality is this surface in this case instead of the disconnected one. And this situation is interesting because according to entanglement wedge reconstruction, the local operator algebra of the boundary subregions should be able to reconstruct the region beyond the causal wedge. And nevertheless, this sort of implies that there are operators in this subalgebra which manifestly violate bulk causality, in the sense that applying these operators close to the asymptotic boundary of ADS could lead to the creation of a particle in a region which is causally inaccessible from this boundary subregion. And an open problem is to try to characterize whether there is a distinction between the reconstruction, the causal wedge, and the reconstruction beyond the causal wedge. So this is where the idea of the Python branch comes in. The basic idea is that there is a distinction in the reconstruction based on quantum computational complexity. So the idea is that the region, reconstructing the region beyond the outermost QES is computationally more complex. Okay? I will try to quantify this statement. But let me just represent the general situation, which occurs whenever the entanglement wedge extends beyond the causal wedge. So in general, we have two subregions, A and A complement. These can be full boundaries, these can be parts of boundaries, so don't take this picture too seriously. And in these situations, the entanglement wedge extends beyond the causal wedge, which means that there is some non-globally minimal quantum extremal surface here, which I will call the constriction, which delimits the region of causal accessibility. Okay. And beyond the constriction, there is the true globally minimal quantum extremal surface, which delimits the entanglement wedge. And since these are locally minimal surfaces, there must be a quote-unquote maximum surface in between the two. This maximum surface, I will define it more precisely later for some particular situations, but for now let's just call it the bulge and think of it as a maximal surface. So the main idea is that the reconstruction of operators outside of the outermost quantum extremal surface, outside of the constriction, is simple. And this was shown by Arvin, Jeff, and Mehta 1 year ago, 2 years ago actually. And the idea is that one can sort of generalize HDL reconstruction to access all this region, but sort of this process fades once one reaches the outermost extremal surface. So this region can be reconstructed simply with understand as simple the HDL sort of reconstruction in terms of local conformal primaries of low conformal dimension. Now, the main idea that the Python branch conjecture is trying to convey is that the reconstruction beyond this surface is complex. Okay. In particular, the proposal is that the complexity to reconstruct operators beyond the outermost extremal surface, is geometrized by the generalized entropy of the bulge quantum extremal surface. The proposal is that the complexity to reconstruct the interior scales exponentially with this particular exponent. So the exponent is the difference in generalized entropies between the bulge and the constriction. So basically this jump in areas for the classical case. Okay, let me now motivate the heuristic reasoning behind this conjecture. So the idea comes from tensor network models of CFT, where the geometry or these slides gets modeled as a tensor network, which is some way to parameterize quantum states in many body quantum systems. And the main idea is that well, I'm going to forget about the bulk effective field theory. I'm just going to consider this sort of tensor network as a map between the minimal quantum extremal surface to the boundary. This is the bulk to boundary map that we care about. And the idea is that this map is geometrized by the geometry of the slide that you live in. And in particular, it can be decomposed in smaller maps. So this map is just the composition of a map which takes you in the tensor network from the minimal cut to the bulge. Then the second step would be to go from the bulge to the constriction, and the last step would be to go from the constriction to the boundary. So in the tensor network, each cut represents some microscopic auxiliary hyperspace, and that's the reason why we can think about this decomposition. In gravity, this is less clear, but let's just take the intuition from tensor network. So the main idea is that if you go from a larger hyperspace to a smaller one, under genericity assumptions of the map is approximately co-isometric. Whereas if you go from a smaller cut to a larger cut, the map is approximately isometric. So co-isometric means that the inverse map is an isometry, so the map can be thought of as an orthogonal projection or a measure. Sometimes the term post-selection is used one information. So given this tensor network, reconstructing the map or trying to reconstruct the entanglement web corresponds to acting with operators in the boundary state region A, which are able to undo this tensor network. And the idea is that undoing the exterior is simple because one can just apply the inverse, the part of the map which takes you from the constriction to the boundary. And this basically gets rid of this part of the tensor network. You're left with this other part, which is the map which takes you from the bulge to the constriction. And this operation is thought to be simple because this operator that you have to insert doesn't contain exponentially many gates. It's just some sort of polynomial complex operator that you can access in the region. On the other hand, if one tries to do this for the second part of the map, one ends up with something which doesn't give the identity. What this means is that basically this part of the map post-selects some quantum information, so it takes you from a bigger hyperspace to a smaller one. So if you naively were to act with this inverse, you wouldn't end up with the identity because this product is just some orthogonal projection. Okay? So physically what this means is that this is sort of like a measurement, and you cannot undo measurement unitarily by acting on few qubits. So the protocol that they provided in the original paper was to grab a bunch of additional qubits, ancilla qubits. The number of qubits that one needs is precisely given by the difference in generalized entropies of the bulge cut and the constriction cut. And then once we've considered these additional qubits, the goal is to find some unitary acting on the full bulge cut, which has the effect of post-selecting these qubits to the zero state times some physical state that comes out from the constriction for all the physical states that live here in the bulge. So there might be other states in the bulge which are predicted to zero. This unitary, what it does for those states is that it gives you something which is not the product of the zeros for the zeros. So basically this unitary is trying to reproduce the measurement, the original measurement performed by this part of the tensor. And under genericity assumptions for this post-selection, it's believed in quantum information, and this is the protocol that they provided in the original paper, that the optimal way to build this unitary is through some protocol which is called Grover search, which I will not explain in this talk. But the idea is that the number of steps that one needs to build this unitary scales exponentially with the number of post-selected qubits. Okay? So the precise exponent in Grover search is the exponential of the difference in entropies of the two cuts divided by 2. Okay? And once we've reached this formula has a direct translation into semi-classical gravity once we identify the entropies of cuts of the tensor network with generalized entropies of surfaces in gravity. So this is the motivation behind the flash, which probably most of you already knew. So for the rest of the talk, I will tell you about a particular case of Pythons. So that I will just restrict to time reflection symmetric Pythons. Basically, what this does is to make the problem much simpler because one doesn't need to worry about time dependence at all. And I will also restrict to classical situations in which all of the quantum extremal surfaces are classically extremal. And yeah, this is what Midjourney thinks of gravitational Python Flash. This, of course, is influence of Ryan. But yeah, so for the rest of the talk, I will basically try to define what the batch is more rigorously for these particular cases. And I will tell you about some properties which are really surprising about these surfaces, which also have important consequences for the Python Flash conjecture. And I will end with some conclusions and open questions that I would like to understand better. So let me start with some basic facts about extremal surfaces. So I will just be restricting to time reflection symmetric Cauchy slices. So my full space will be some slice on space-time. A hypersurface on this space is just a codimension to surface on space-time. And this surface is said to be extremal if the extrinsic curvature when embedded in this ambient space vanishes. The reason is that the first order variations of the area are proportional to the trace of extrinsic curvature. However, to second order, the area of extremal surfaces changes, and the second order variation of the area is controlled by some differential operator in the space of deformations of this surface. And this differential operator, you can think of it as some Schrodinger type of operator in some L2 L-squared space of functions. And in this particular case, for the area, it just has this form. So it's basically composed of the induced Laplacian on the surface. Then there is this term which is proportional to the Ricci tensor contracted in the normal directions to the surface. This is the ambient space Ricci tensor. And then this third term is just the square of the extrinsic curvature. So
just in your terminology notation. So by n you mean something like a Cauchy surface?
Yeah, exactly.
And x is a codimension two spatial surface?
Yeah. It's a hypersurface on this Cauchy surface.
Yeah.
Yeah, so I won't even mention time in this talk. Only towards the end. So these to second order, the variations of the area are given by this differential operator. This differential operator turns out to be, well, one can check it explicitly, turns out to be symmetric and real. So what this means is that this differential operator has a real spectrum on this space of deformations of the surface. And one can define the Morse index of a surface, of an extremal surface, as the number of negative eigenvalues of this operator. So when we say that a surface is locally minimal, that's the same as saying that the index of this surface is 0. Okay, so in differential geometry, there are mathematical theorems that guarantee the existence of index 1 extremal surfaces between two index 0 extremal surfaces. This is what I'm going to tell you about now. So let's assume that we have the situation that we care about in the Python Flash story, which is a region of some Cauchy slice, this is the blue region, which is delimited by two index 0 extremal surfaces, which are on the same homology class. Okay? So these surfaces can, in principle, have some boundary, and they have to share this boundary because they are on the same homology class relative to this boundary. And the mathematical theorem is basically that given this setup, there must exist an index 1 extremal surface in between these two index 0 extremal surfaces. So index 1, remember, yes?
Just to clarify, so for these surfaces, isn't the index dependent on a specific choice of curve?
Yeah, so
there's one and one curve, yeah, how do you...
You mean, so yeah, the index could depend on the choice of the Cauchy slice. Yeah.
I guess you're when you say that the index of a thing, actually, can you go back one? Sorry.
Yeah.
Yeah, so this operator,
yeah.
I guess the number of negative eigenvalues, it seems to me that it's going to be dependent on a point on x. Like, you know, if I'm looking at, yeah, it'll vary for different points.
No, so the point is that this is a differential operator, and So it has some eigenvalues and some eigenfunctions. So basically, when you apply this operator to an eigenfunction, it gives you a number times the eigenfunction at all points.
I see.
So it doesn't depend on the points. Okay, so this is the mathematical theorem that guarantees the existence of an index 1 extremal surface. Index 1, remember that what it means is that it has one negative, this Jacobi operator has one negative eigenvalue. So this surface is maximal only in one direction in the formation space. In the rest is a minimal surface. Yeah.
And there's no, to your knowledge, no theorem proving anything like that for other than index 1.
Yeah. Well, that's a good question that we were thinking about at some point. There could be a situation in which in between two index 1, there must exist an index 2.
Yes.
But there you have to also ask for additional conditions on the index 1 surfaces. The reason is that index 1 surfaces are maximal in one direction, so you have to sort of align this direction on both cases in order for the sort of other maximal to be in between the two. So it's not that trivial, it's not that general, but in principle, yeah, there could be. And this surface, the mathematicians construct it by a minimax algorithm. So the idea, the rough idea, is to foliate this region by hypersurfaces, so in this way, by these great hypersurfaces, and find the maximal area hypersurface for a given foliation. And then the second step is to minimize our foliations. And this basically splits some surface, which is always guaranteed to exist and corresponds to the bunch. So actually mathematicians use a more sophisticated language and more sophisticated concepts. So they don't talk about foliations, they talk about sweep outs, which are sort of generalizations of foliations in which a point in this region could be contained in two hypersurfaces. So the slices could just go forward and come back again multiple times. And they could also split. Okay. So the minimax definition in terms of foliations was given in the original paper, and throughout our work we are assuming that the definitions that the mathematicians gave actually corresponds to the same definition.
Just to understand.
Yeah.
You're saying if you want to prove this is an actual theorem, the thing that you should minimax over is these sweep outs?
Yes. So the minimization is not over foliations, it's over some generalization of a foliation, which is a sweep out, which basically is it's a generalization in the sense that the hypersurfaces can bend forward and backward.
But does it matter for us which it is? I mean, why don't we just use the definition that the mathematicians use to prove the theorem?
Well, because it's, yeah, that's a good point. So, in general, it's difficult to work with these sweep outs. We want to prove lemmas, for example. And moreover, it's not like, we thought that, allowing more freedom for this foliation doesn't help in minimizing the area of a surface. So probably, even though we weren't able to prove it previously, the definition that the mathematicians gave can be translated, at least at the physicist level of rigor, to the same definition.
So in other words, it's not plausible that the only way to find this XP would be by sweep out. You can find it that way, you can also find
I also thought mathematicians, they weren't really proving stuff using sweep outs. The technology used to prove powerful results is like varifolds and shit like that.
Right.
Very abstract and disgusting. And sweep outs are already like it ends up in lower than 7 dimensions or something. You can prove it ends up being like a relatively nice object at the end of the day.
Okay.
You can sort of sweep out what do in certain circumstances, but to actually prove things, then you don't try to prove things about sweep outs, you prove things about varifolds and blah blah blah. Geometric measure theory.
Yeah, so it's much more complicated than what I'm going to tell you about, but let's assume for a second that the definition in terms of foliations makes sense.
Sorry, but so you're allowing for like splitting stuff like
I
that?
think so,
right?
yeah. In this variable story, you are allowing to
And you
no,
are also.
no.
So you're not allowing topological changes
No.
along the way? I
No.
see.
Okay. So why does this surface interest us? So first of all, this bulge surface defined by the minimax algorithm is the only surface which is guaranteed to exist in this setup. So that's one reason. And the second reason is that it has a nice tensor network interpretation in the sense that if we interpret this region here as a tensor network, the foliations, so this minimax has a nice interpretation in the sense that we foliate this tensor network using different cuts. And now we want to undo these tensor networks by applying unitaries layer by layer following this foliation. So the max basically detects the amount of post-selection given a foliation of this tensor network, and the mean is just the optimal way to, the optimal foliation to undo this tensor network in this layer by layer way. Okay, so obviously trying to minimize our foliations is pretty complicated. So what we did in our paper was to prove the following level. So let's consider the same situation where we have two index zero surfaces delimiting some region here. And we were able to prove that under these circumstances, if there is no other index zero surface in between these two, then the bulge is the minimal area index 1 surface. So the way to identify the bulge is basically to identify all index 1 extremal surfaces in this region, and then pick up the minimal area 1 among these. And in the rest of the talk, I will try to argue that many properties which are always assumed to be true for minimal surfaces, like the RT, are not true for this bulge surface, and this has important consequences in the Python functional structure. But before that, let me just show you some examples of Pythons. Let me just focus on vacuum AES3 and vacuum AES4 for simplicity. So this example was originally pointed out in the original paper, the original reference, and it consists of the case of two intervals in AES3 in the connected phase. So in this case, as I told you before, there are two locally minimal surfaces, and if the intervals are big enough, the entanglement wedge contains this region, which is beyond the causal wedge. And it turns out that in this case, the bulge is sort of singular, since it consists of two self-intersecting geodesics. And this surface, well, first of all, if you want to apply the sort of reverse theorem, you have to be careful because this surface is singular. But the idea is that there are two independent deformations of this surface. Sorry, there's only one independent deformation, two different directions, but it's the same deformation, which decreases the area of this surface to second order. And that deformation is to basically cut this cross. So you can cut it two ways. You can cut it horizontally in such a way that the surface decreases its area and becomes the disconnected minimal surface. You can cut it vertically, where the surface becomes the RT. And in both directions, the area of the surface decreases to second order, and in some sense, one can view these both directions as the two sort of different directions of some deformation, of a single deformation. In that sense, this surface has index 1. Now, in higher dimensions, these surfaces are completely smooth everywhere. So let's consider the case of two disks in vacuum AES4. So this is the Poincare ball. And if the disks are big enough, the entanglement wedge is also in the connected phase, and the Butakanali is some catenoid here. There is also a disconnected locally minimal surfaces here. And in between the two, there is another catenoid in red, which is the bulge. we were able to show by studying the perturbations, the spectrum of deformations of this surface, that this surface has actually index 1. Okay, let's now analyze some properties of these batch surfaces given our prescription to find them. So let's assume that we have some compact space. As it turns out to be the situation in all of the top-down constructions of ADS-FT. So let's assume that we have an ADS 3 times S1. In that case, typically what we assume about minimal surfaces is that the surfaces, if the metric is of product form, the surfaces will completely wrap the internal space, and they will just factorize as well. So this is what happens if we add an S1. Here the S1, I just represent it as an interval. You just need to think of it as identifying the two ends of the interval. So the Ryuta canalis here are just the product of the Ryuta canalis in ADS3 times the interval. On the other hand, I don't know if you can appreciate it, because the resolution is not great, but the batch surface basically doesn't wrap the internal space, and it resolves this singular cross. So the topology of this batch surface in this case is a sphere with 4 punctures. And this surface, in the case of flat space, it has been studied by mathematicians a long time ago, and it's called the second shared surface.
In the ADS4 case that you were showing on the previous slide, this is also a smooth surface, right?
Yes, this was already a smooth
They're
surface.
sort of more obvious that it's smooth.
Yes.
You're saying even if I...
Yes. Even if you start with the ADS3-1, and if you add an S1, it becomes smooth. And this scale of resolution is typically the asymptotic scale of the S1, which in top-down constructions is of ADS size. So this sort of effect is relevant in
So I
microscopic.
suppose to take away from this that in physics applications that I would care about, I never have to worry about these.
Yes, yes. Also, the fact that the area of the general entropy of this surface knows about the particular microscopic theory that you are working with. In the sense that, well, if you have a different theory with a different global symmetry, you will also have a different internal space and a different sort of area for this surface. On the other hand, Ryuta canalis and minimal surfaces are only know about the time structure of the ground state, which is sort of universal, doesn't sort of care about the internal space.
This thing spontaneously breaks the symmetry of the S1, right? So it's really a degenerate set of surfaces that can move the whole around the S1.
I don't think
Stand
so.
up picture correctly. Okay.
That's a good question. I don't think so, but yeah, we didn't check. I don't think so.
Well, what would fix it? The input data don't break the symmetry, right?
Yeah, that's a good point. Yeah, I have to think about that. Yeah, it could be a spontaneous breakdown of the next one.
But what do you think is a continuous boundary?
You know what it breaks?
Did
If it's spontaneously broken, then
Yeah.
I think it has to be continuous.
Yes, what is? No, but, oh, sorry, I'm just imagining like a one-dimensional mixing and potential between things. But
Yeah.
this is the one, I see.
Yeah, it's a continuous symmetry that's being broken.
Yeah, yeah.
So we don't really know what, are we supposed to integrate over this in some way? Or?
Probably. That's, yeah.
Yeah, I will
I mean, it
show.
was an RT surface, I think.
Well, no, these services, yeah,
Yeah.
much more obvious what to do.
So, one thing here I don't know is relevant. So in that case, on the left side, I think if you consider quantum extremal surface, it would already not be singular.
Right.
So, I don't know if that now, if you apply that to the right, like, does that help with anything? Pick up one? I don't know.
Well, yeah, so there's different ways to resolve this similarity, as we say. The quantum case would help, but this is already non-singular at the classical level, so adding, you mean like adding quantum fields here? It doesn't do anything.
Yeah, because you're saying that even, so I can draw a smoothed out version of that,
Right.
that would be selected in the ADS3 case if you add quantum corrections. I can draw it there as well.
Yeah.
You would be saying that that's not the right surface, this other one is.
I think this one would dominate, right? Because if we take the semi-classical limit, all the quantum corrections would go away, whereas this is some classically different thing.
Okay, so those are like, I guess, there must be index 1, but not the smallest
Is
one.
that obvious? I mean, the reason,
Yeah.
let me just check. So in the ADS3 case, right, the reason that you're saying that if you include quantum corrections, it smooths them out, is presumably that there's some corner contribution to the entropy that is not worth paying for. It's better to increase the area a little bit or something. Right?
Yeah.
But then why couldn't that happen here as well? Even, I mean, it will continue happening in the T goes to 0 limit. It would just get closer. I mean,
But I think this thing is classically better, right? That's some like quantum decrease. Yeah, this is a classical decrease. It's always going to be larger. I think it is an even index. Like if you just took the AES3 surface crossed with S1, that wouldn't, like classically that wouldn't even be index 1 now, right?
No, it would be index infinite actually.
Yeah.
So,
if you could-
sorry, which one? The classical one?
The classical
one? No, I mean the smoothed out one.
Yeah, it's not obviously the smoothed out one would be index 1 either.
But not index infinite, right?
Sorry?
But also not index infinite.
No.
So, okay,
Okay.
the reason why it's index infinite is because, you know, if you have an S1, you can do Kaluza-Klein reduction of the modes on this one. And these have some positive eigenvalue, but then the original one has an infinitely negative eigenvalue. So the sort of S-wave mode has minus infinity as an eigenvalue. So all of these Kaluza-Klein tower is negative. If you resolve that, it depends on like how many of these Kaluza-Klein modes survive.
Right.
But you need only one of them to survive in order for this to be a candidate.
Yeah, I know, yeah, I guess I would be curious if the other one is ruled out by not being the smallest one or just at the level of index. Or what was your rule, sorry, the smallest one? Your rule
Yeah.
is the one index ones pick the smallest one.
So, but in this case, as Jeff was saying, in principle, there's an infinite family, which all of them have the same area. Once you project out onto the ADS3, all of them are the same. So, okay, let me tell you about another example of spontaneous symmetry breaking. So let's start with a time reflection symmetric, one-sided, semi-classical state of a black hole. And here I'm drawing the Tenor diagram, and I will be just focusing on the time reflection symmetric slides. Here I'm assuming that the space-time caps off smoothly, so this is R equals 0. And probably there's some matter here supporting the geometry that I'm talking about. So in this case, I'm assuming that there are three extremal surfaces on this surface. One is the apparent horizon, second one is the empty surface, and in between the two is supposed to represent the induced geometry of the initial time slice. In between the apparent horizon and the empty surface, there is a naive sphere, which is maximal, okay, in between these two surfaces. So here I'm assuming that everything is spherically symmetric. The CFT is based on a sphere, and the state of the CFT is spherically symmetric. Now, this naive surface, if the curvature of the lunge is very prominent, it has index larger than 1. The reason is that different modes of the deformation of the surface have negative eigenvalue, decrease the area to second order. So the true patch in these situations spontaneously breaks spherical symmetry into some subgroup, and there are additional zero modes, as Jeff was saying before with the S1 case, which connect this infinite set of bulges. These zero modes are associated to unbroken symmetry generators.
So what was the reason to identify bulge as index 1 surface? if that's the case?
So the reason from the point of view of the geometry is that it's the only surface that is guaranteed to exist, always. From the point of view, of the tensor network is that, well, if you chose the naive spherically symmetric foliation of this tensor network, the amount of post-selection that you will need to overcome will be bigger than if you chose some foliation which breaks spherical symmetry, which contains this surface as the maximum area.
If you're saying if we buy into the minimax prescription,
Yeah.
the red one will be selected automatically.
Yeah.
And what you mean by curvature of the largest the curvature is sort of orthogonal to the
Yes, there's
naive bulge is stronger than
Yes.
convoluted.
Exactly. So these two scales
You can
compete.
easily arrange this.
Yeah, you can easily arrange this if by putting some shell or whatever.
Yeah.
Yeah. Okay, so this was about continuous spatial symmetries. This is also consistent with Arvin, Jeffs, and Neta's paper, where the bulge was another minimal QESs were found to break time reflection symmetry. And actually, this connects with the discrete spatial symmetry story. So let's assume that we start with some situation, some state which has discrete spatial symmetry, like a multi-boundary wormhole state of the three-dimensional black hole. Here, just drawing three boundaries. The geometry is completely completely symmetric with respect to permutations of these boundaries. However, if one tries to use the minimax prescription for the full boundary, so the RT surface for the full boundary is obviously empty because this is a pure state. The constriction for the full boundary is the union of the three horizons. And the bulge for the three boundaries breaks the permutation symmetry of the state into a sim2 subgroup. So it basically corresponds to a self-intersecting geodesic which wraps around two horizons, and additionally the constriction of the third one. Okay. So what this means is that if one takes the Python-Lagrange conjecture seriously, the complexity to reconstruct the interior with access to the three boundaries is exactly the same as the complexity to reconstruct the interior with two boundaries. The reason is that the bulge for the three boundaries is the bulge for two, and additionally the constriction of the third one. So this is, I think, a non-trivial feature of the conjecture, which tells us that in geometric states, this also happens for two-sided states. The complexity of reconstructed interior is exactly the same whether we use one boundary or two. On the other hand, we know that with access to two boundaries or three boundaries, there are some probes of the interior. Like for instance, if we're trying to compute two-point function between left and right, this is supposed to have some information about the length of the one. The Python-Lagrange conjecture sort of implicitly assumes that this sort of information won't help at all to decode the local physics of the interior. Okay, let me now tell you something which has more importance for the outcome of the Python-Lagrange conjecture, which basically happens when trying to consider extended black hole interior. So in this setup, consider planar black brane in 1 + 1 dimension. Let's consider a state of this planar system which contains a Python flange. So the metric on the initial slice is just d rho squared plus r rho dx squared. And R of rho controls the profile of the transverse space along the geometry, and we will choose R of rho for it to contain a Python. What this means is that A is the asymptotic boundary, R of rho has some minimum at some point here, then it has a maximum, and then it has another minimum. This second minimum has a smaller value of R than the original. So we will also choose to regularize the transverse space with some cutoff by inserting some end of the wall range here, which are sort of tensionless. So they don't modify the geometry at all. They're just purely cutoff that we decide to impose. And given this, we will try to find what the constriction, the RT, and the bulge are. So the RT is always this surface, which sort of meets the end of the wall branes perpendicularly. The constriction is always the apparent horizon of the black brane, which is here. And in between the two, there is, as we said, the naive maximum surface, which meets the end of the wall branes perpendicularly as well. So what happens if we increase L is that this surface develops additional negative modes, so it cannot be the true bulge. And it starts to break the set 2 reflection symmetry spontaneously. So there's actually two surfaces now, which bend and probe the interior geometry, and these correspond to the values. And for very large values of the transverse space dimension, what happens is that the bulge starts to have the constriction for most of the time. So this happens for most of the time, and the region in which they are different is sort of small. It doesn't scale with this parameter L. So what this means is that if we take the Python math conjecture seriously, the log complexity to reconstruct this interior, given the operators in subregion A, is just the difference between the generalized entropy of the bulge and the constriction, and this doesn't seem to scale extensively with the size of the transverse dimension. Okay, so it scales as n squared, obviously, because it's a difference in areas, but as n to the 0. It doesn't scale with L. On the other hand, the entropy of this system, the naive thermodynamic entropy of the black brane, obviously scales with the size of the transverse space. So in this sense, extended interiors, this also happens for black holes, for very large black holes, seem to be simple to reconstruct with all of this entropy. So we were originally very confused about this fact. We thought that it was a bad thing about the conjecture, but now we think that we understood why it happens. So it's actually a property of exponential complexity. So let's assume that we have two different systems. We're trying to reconstruct both interiors. Okay? Obviously, the complexity to reconstruct both interiors, given that we know this factorization, so we don't have to act with operators that couple the two systems. This complexity is just the sum of the two complexities. And if each complexity is supposed to be exponential, the sum is dominated by the exponential of the maximum exponent among the two exponentials. So there is some subleading factor, but for our purposes, we don't care about this subleading factor. We just care about the exponent. So it's very reasonable that for independent systems, the complexity to reconstruct the corresponding interiors doesn't scale extensively with the number of subsystems that we have. And for thermal state, this happens to be the case. We have this picture of independent subsystems, but thermal states can be thought of as composed of independent subsystems at the thermal scale. So the prescription is clever enough to realize this and to give a complexity which is not extensive in the system size, a low complexity which is not extensive in the system size. Okay, let me just end with two aspects that I would like to understand better in the future. So the first one is time dependence of this story. So I've been, in my talk, I've been restricting to time reflection symmetric situations in which all of the variations were restricted to this slice. The point is that if we want to analyze the spectrum of second order deformations of an extremal surface in space-time, the associated Jacobi operator will fail to be self-adjoint. So in general, it will contain complex eigenvalues. So this means that we cannot do our classification in terms of the Morse index in general. However, one nice thing is that if we restrict to time reflection symmetric situations, it turns out that the space-time Jacobi operator, so we don't restrict to spatial deformation, we allow for any deformation of a space, of a time reflection symmetric surface. Then the Jacobi operator has a real spectrum, and we can extend this idea of the Morse index to time-like deformation. So we can define the Morse index of an extremal surface lying on a time reflection symmetric slice by two numbers. First one represents the the number of negative space-like modes. Second number represents the number of negative time-like modes. So in this convention, I'm calling negative time-like modes to deformations which make the area increase to second order. The reason is that there is a convention where you have to also include the norm of the deformation, and for time-like vectors this is negative. Okay. So in this notation, 0, 0 surfaces are minimal surfaces. 1, 0 surfaces are bulges. So basically are surfaces which have one negative mode in the space-like direction, but 0 negative modes in the time-like direction. So the area in the time direction decreases. This is what we expect for all of the examples that I've been talking about that we analyzed in the paper. Then 0, 1 surfaces are not allowed by the navigation condition. You can show that pretty easily. And 1, 1 surfaces are sort of surfaces which decrease, have one negative mode in the spatial direction, have one negative mode in time direction. These were the surfaces that were called bounces in this paper by Arvin, Jeff, and Neta. And it would be nice to make a connection between these classifications, classification and their classification, which was sort of more general. Their classification applied to general situations, not only to time situations. But it would be nice to make a connection given that this classification is much more detailed. And as a second sort of comment, I would like to also understand the conceptual story behind the Python branch conjecture better, in the sense that, well, one can ask the following question. So, okay, let's assume that we all buy this tensor network interpretation of the path boundary map. Then, obviously, in tensor network and in any sort of reasonable model of quantum computation, the complexity of doing something on a hyperspace must be upper bounded by the exponential of the entropy of that hyperspace. So let's focus on this part of the boundary map, which takes us from the minimal surface to the constriction. So no matter what this isometry is, this approximate isometry is between the minimal surface and the constriction, its complexity cannot be larger than the exponential of the entropy of the constriction.
Shouldn't it be order e to the 2 times the entropy?
Well, yeah, there could be factors of 2, yeah.
So then I think, because the maximally complex unitary has a complexity like 4 to the n, where n is the number of qubits. So then I would have thought this only applies if the bulge is 4 times the size of the...
Okay, yeah. Yeah, there could be like factors here. I'm just making the yeah, so for a unitary it would be exponential of 2 times the entropy, and yeah, I was just thinking of states. But the main point I wanted to make is that, well, if in this decomposition of this map, if the entropy of this hat is larger than twice the entropy of the constriction, then the complexity sort of predicted by the Python branch conjecture exceeds this bound. So it's exponential with some exponent which is much larger than this one. So this bound is sort of useless in the sense that the prescription presented by the Python branch conjecture to undo this tensor network based on Grover search and the ancilas is not optimal. And contrary to what happens with exponentially complex states without a Python, like for instance the state of a two-sided black hole at exponentially long times, these situations can be sort of easily manufactured by adding, a bunch of matter here, which makes this bulge to be larger than some factor times the area of the constriction. So in these situations, at least from a tensor network interpretation, there should be an optimal or a better way to think about this interior in terms of a tensor network, which is shorter than expected. And yeah, the question that I want to understand is whether this means something in semi-classical gravity or not. Thank you.
Just on that last point, so you're saying if the bulge area is more than some order 1 number times the area, then the Python solution overestimates the complexity.
Yeah.
The conjecture overestimates the complexity.
Yeah. I think we've sometimes thought in the past about putting this as a qualification of conjecture, but sort of never bothered to write it down. Like it's a sort of obvious qualification. But
It's a very easy thing to arrange, and particularly in all of the pictures, it looks like that.
Yeah, yeah.
I don't think in all of the pictures.
I think in most of the pictures in this talk.
It could be, yeah, it seems simple to arrange situations in which you can do that. The question is whether there exists some other representation of the same state in terms of something which looks like a geometry without a bus or something like that.
I mean, I guess it's also happened like in the case if your prescription is right for the de Sitter kind of setup.
Yeah,
exactly. I somehow didn't fully appreciate how quickly that actually kicks in. Yeah.
Yeah, I mean, like the original context was an evaporating black hole, and it never kicks in for that. It's the appetizer always gets bigger. Yeah.
So for instance, in vacuum, this obviously never happens because all the areas are sort of infinite, and the differences are like finite.
Yeah, so let's see, what should the factor be if it's not 2? I think isn't it that the difference between entropies should be less than 4 times the entropy of the small ones, so it's actually that it needs to be 5 times the big. So, like the pictures are again.
Okay, I think you're satisfied.